In this lecture, we will see how we can define the global properties of the spacetime, such as mass, angular momentum, and other charges. So, we will start by seeing how we can define the conserved charges in a curved spacetime. And we will use some formulas from differential geometry which involve the Hodge duality. This will allow us to rewrite some differential operators, such as divergence, or the curl through the differential forms language. So, we introduce the Hodge duality as an operation on the P forms in a d-dimensional spacetime, where the epsilon mu1 mu d minus p nu 1 nu p is the Levy-Civita pseudotensor, so it's a totally antisymmetric. So it's totally antisymmetric as in its indices, and for 1 to d, it equals to plus square root of the modulo of the determinant of the metric. The standard property then follows that the contraction on the set of p indices of one pseudotensor and another would give us the following identity. This then allows us to show that the Hodge duality is an involution or an anti-involution, depending on the signature of the spacetime and the dimensionality of the form, and the rank of the form and the dimension of the spacetime. So, as in the classical field theory, the definition of a conserved charge, starts with a conserved current. So, let's say we have a conserved current, which in the differential form language is the same as stating that the Hodge duality of the four currents, seen as one form, is closed. If you're not familiar with the differential form language, this remains a good check of the given conventions. So we can define the charge on a spatial hypersurface, on a space-like hypersurface sigma, as follows. So we have sigma as space-like hypersurface, and we can define the charge as the integral over the Hodge dual of the conserved vector, of the conserved current. So, in the usual notation, this is the same as 1 over 3 factorial if we are speaking about the four-dimensional geometries, because J is one-dimensional, and the Hodge duality of J would be rank 3 differential form. So we have the 3 factorial from the differential form times the sigma of star G mu nu rho dx mu dx nu dx rho, which equals to minus integral of sigma over star J mu new row dx new dx new dx row, where mu less than new less than row, because here there is a 3 factorial repetitions, and by picking mu less than new less than row, we cancel the 3 factorial factor. So don't worry if this notation is not very familiar for you, because then we will calculate the electric charge for the Reisner's from black hole. Okay, so why is this charge conserved? So let's say that we have 2 space-like hypersurfaces that together enclose some region of the spacetime. So let us have the following picture. So let this be the sigma, the space-like hypersurface sigma, and let this be the sigma prime. And together they enclose the region of the spacetime R. So in other words, dr is sigma prime minus sigma. This is related to, well, to the definition how we go around the contour. So we can say that we go in the clockwise direction, and then we go back along sigma, which then inverts the orientation on sigma. So we are going in sigma prime minus sigma to complete the contour. Good. So now let's see the difference of the charges on sigma prime and on sigma. So we naturally have that Q calculated on sigma minus Q calculated on sigma prime equals the integral of sigma, the integral over sigma prime minus sigma, because there is a minus sign in the definition of the charge, times the Hodge derivative of J, which is the same as integral over the boundary dr, which is the same as, by the nature of the Stokes theorem, that relates to the integral over contour to the integral over the volume. The integral over the surface to the integral over the volume, and similarly, well, the green theorem that relates the integral over the contour to the integral over the surface within this contour. We have that this is the same as the integral over the space-time region R of d star j. But as we said, the current is conserved and d star j is 0. So this is 0. In other words, the integral over any two possible space-like hypersurfaces that enclose closed region of a spacetime is conserved, is the same. So the moral is that charge is conserved. We of course want to do something more. Instead of working with the slices of the spacetime given by the space-like hypersurfaces, we want to be able to conveniently calculate a conserved current. For for a space-like hypersurface through its boundaries. So, in other words, we want to define some asymptotic charges by working with the boundaries of this, by taking such a space-like hypersurface which has a boundary itself, and we will integrate over its boundaries, so over two-dimensional surfaces at infinity. To do this, well, by the Stokes theorem, the star J needs to be exact. This is not always the case, as we will see in the next subsection. Now, let us turn to a more simple example of electromagnetism and electric and magnetic charges. So, let us consider electromagnetism. So, the Maxwell equations are given by the Bianchi identity and, well, the Maxwell equation itself. Where J is the electromagnetic current, which is a vector or dually a one form, and F is the field tensor. So the Bianchi identity states that the exterior derivative of F is 0. In other words, this is the same as writing d mu F nu rho equals 0. And this is the same as writing that F mu equals plus 4 pi, no, minus 4 pi J nu. If you have never done that, it's a good exercise to check. So the Bianchi identity tells us that F is a closed form, and by the Poincare lemma from differential geometry, every closed form is locally exact. So locally there exists such function, such one form A, such that it is the electromagnetic potential of the electromagnetic field. So the important consequence of the Maxwell equation is that for on-shell configurations, the current is the Hodge dual of the current is conserved, because so d squared of star F so is of course 0, and this is the same as so the current is conserved. Using the previous definition, it is then, we can then write minus integral over star J equals 1 over 4 pi G star F. So therefore, if you take sigma to be a closed manifold, closed manifold means that compact without boundary. Then this integral would be 0 by the Stokes theorem. So naturally, we want to take sigma. We want to take sigma to have boundaries. To take boundaries naturally at the asymptotics. So by the Stokes theorem, this is the same as star F the same as the integral over the boundary of sigma over the star f. Let us now do the calculation for the Reisner-Nordstrom. So we naturally take sigma to be the constant time slice, and let us take sigma r to be its subregion, bounded by the value of the radial coordinate as r. So notice that technically we do not include the singularity into the spacetime. So our spacetime ends. So our spacetime ends at r ends at r equals 0, and the singularity itself is not included. So we have the range of coordinates r going from, so r greater than 0, but less than or equal to some value r. So we can then, so in other words, the boundary of d sigma r is the singularity, and well, the boundary r. Sorry, this should be chemical 0. So the Maxwell field was given by minus q over r dt, and from this it follows that the gauge field strength is q over r squared dr dt, and they anti-commute, so dt dr. From this, one can calculate the Hodge dual of f. So we see that star f theta phi is given by square root j f times tr equals r sine theta ftr equals q sine theta. All other components of the star f vanish. So naturally, one can object by saying that, well, the electromagnetic current for the Reisner-Nordstrom solution is naturally 0. So this quantity will be normally 0, and we will get 0 charge. Well, this is not quite so. The reason is, as you can recall from calculus, it all comes from the boundary conditions. So we have the singularity at r equals 0, and this will give us the non-zero contribution. So yes. So the total integral over the star j, which is 0, is 0. and this equals to the integral of star f over the boundary of the sigma r, which has two components. So we have we have 1 over 4 pi of the surface at R, of the two-dimensional sphere at radius R, and we have the integral taken in its principal value over the surface taken in the limit R going to 0. So naturally, we'll take the first term as a definition of the charge, and we naturally have that. Q of sigma r defined as the integral over the sphere of radius r is also the same as the integral over the sphere, which is of the radius tending to 0. So we can see that this is naturally independent of r. We can see that this naturally is independent of r, and this is the integral of star f, and this is the integral of the star, f of the surface given in spherical coordinates. So let us write it more explicitly. We have star f theta phi, and the differential, so which we're integrating is then d theta d phi. We have removed the 1 over 2 factorial factor when going from star f to its components, because we have fixed the order, because we have fixed the order d theta d phi. The second term, d phi d theta, is the same, and it contributes to removing this prefactor 1 over 2 factorial. So this is the same as, this is integral over 2 sphere, and this is the same as 1 over 4 pi integral of q sine theta of d theta d phi, where theta goes from theta to pi, and phi goes from theta to 2 pi, and we therefore have that this is the same as q. So, two things to note here. First of all, as we said, this calculation was independent of the radius, and it works for any kind of surface. In principle, we would prefer to define the charges with respect to the surface at the infinity, with respect to the surface where the radius r is set in the limit to infinity. Secondly, notice that that the parameter of that the Q, which was a parameter of the solution of the Raster-Nordstrom, is indeed the total charge of the spacetime, as we claimed in the previous lecture. Good. So let us then write the definition. So we will call, so let us take sigma HQ, HK, the asymptotically flat end, and with respect to this end, we can define the charges. The electric charge is given by this quantity, Q equals 1 over 4 pi r going to infinity of S to R star F and the magnetic charge is the limit of the field strength itself. Integral over the sphere at infinity of F. So this is it's an exercise to check that Q and P, that the electric charge and the magnetic charge defined this way for the Kerr-Newman solutions are indeed the parameters Q and P of the solution. So now we want to define the total mass and the total angular momentum of the spacetime. Let us recall how do we define the same things in classical mechanics. So there, by the Minota theorems, the conserved charges are related to some symmetries to some classical symmetries, for example, the time translations or the axial symmetry of the system. So here, in the gravitational setting, we will extend this construction and show that for any Killing field, which generates an isometry of the spacetime, we can define a conserved charge. So this was done by the Komar, and we will call them Komar charges. So first of all, we can follow the rather naive idea of taking the conserved charge to be the Killing vector field itself. So if you recall correctly, the Killing field equation is given by d mu k nu equals 0. So in particular, it follows that the divergence of k mu vanishes, and k mu is indeed a conserved current. The problem with such construction is that while the star k is indeed 0, while the star k is indeed closed, it's not necessarily exact. So it's not necessarily d of something well defined. Therefore, we cannot use our Stokes argument to take the integral of a two-dimensional sphere at the asymptotic flat end at the infinity. So we need to come up with something better. So we can actually come up with the combinations of the killing field contracted on the stress tensor. So let us consider this. So let us construct the conserved current as the contraction of the killing field K nu on the combination of a stress tensors, stress energy tensors. So naturally, since d mu t mu nu is 0, then it follows that the current is conserved. Furthermore, we can show that this current is we can show that the Hodge-Dual of this current is necessarily exact, and we can relate it to a geometric feature of the spacetime. Well, at least on the Einstein equations. So let us use the Einstein equations here. So this is the same as, well, up to the factor of 8 pi. J mu equals to minus 2 Ricci tensor contracted on K nu. And we are using, so we're going on shell. We're using Einstein equations. And this thing can be rewritten by the feature of the killing vector field lemma. So the killing field lemma. The killing field lemma relates the killing field lemma relates the second covariant derivative of the killing field to the curvature tensor. So, if you recall from the previous lectures, we had that for any vector field, d mu nu is the same as r rho sigma mu nu for any vector field. For the killing field using the killing field for the killing vector field using the killing vector field equation, we can then show a simpler statement. We can show that the mu nu K rho is the same as rho nu mu sigma K sigma. So showing this statement is an exercise, and hint that we are using first we are using here, first of all, the killing field equation, and secondly, we're using the Bianchi identity to exchange the order, the Bianchi identity nu sigma equals 0, the algebraic Bianchi identity, to exchange the order of the indices. Okay, so by the killing field lemma, this is the same as minus 2 d nu t nu k mu, where this term is effectively a Laplacian. And Laplacian is a divergence of something, so we can naturally write it as star d star of something of dk. So checking the factor here, it should be 1, is also an exercise in checking our differential geometry, in checking our Hodge dual conventions. So in other words, we have just shown that the Hodge dual of J mu is exact, and the star J equals to 1 over 8 over pi d star dk. We can then define the charges by q equals minus sigma star j equals minus 1 over 8 pi integral over d sigma star dk. So notice that this is an entirely geometric construction. We are using here only the Killing field. So also notice, well, so we have defined this charge and this charge for a given Killing field, and the nature of this charge would depend on the Killing field we are considering. So if we are taking a time-like Killing, time-like Killing field, we can therefore define the mass of the spacetime, and if we're taking the axisymmetric field, we're defining the angular momentum. So we can therefore define the Komar mass and the Komar angular momentum for K being the stationary Killing field, d over dt, and mg over g phi. Good. So, again, as for the electromagnetic current, for vacuum solutions, the Ricci tensor is 0, and therefore the current we are defining here is 0. The situation is entirely similar to the electromagnetic field. So since for black holes we have a singularity which is excluded from the space-time, we have two natural boundaries. And one can say that the mass and the angular momentum are effectively localized at the singularity, at the inner boundary of the space-time. So one can similarly write it as the distribution of the mass for the Schwarzschild solution in the distributional form as a delta function. With the pike at 0. Okay. So one can check that for the Kerr-Newman solution, the Komar mass and the Komar angular momentum coincide with the parameters that we have introduced in the previous lecture, with the parameters of the solution. So finally, in non-asymptotically flat case, these integrals will be divergent, may be divergent. So we can subtract to renormalize them, we can subtract the divergent paths. So, for example, if we're considering asymptotically local ADS solutions, we can subtract the integral over the pure ADS to get some finite value for the mass, to get some finite value for the charges. This procedure is covered in more detail this procedure in more detail is called the holographic renormalization. Next, we will see how to define the charges when we don't have a global killing field in our space-time. One of the benefits of the Komar construction was that the charges were defined in covariant, in a geometric way. However, this construction only works when the solution has the corresponding killing fields. So, what if we consider a more arbitrary spacetimes instead? What if we consider, let's say, a gravitational wave solution, which doesn't have an axis symmetry, which has neither axis symmetry nor. So, what happens if we consider more general spacetimes? For example, if we consider a gravitational wave background which doesn't have a stationarity. In this case, there are several constructions conserved for the asymptotic charges. So we will stop on the ADM construction for the Arnev-Deser-Meissner construction, because it's more explicit about the asymptotics. In other words, since we consider asymptotically locally flat spacetimes, and namely, since we consider the asymptotically locally flat spacetimes, we have the asymptotic killing fields defined in the neighborhood of the infinity. And therefore, we can define the charges with respect to them. This is a very physical setting because we, at the planet Earth, identify ourselves with the asymptotic observers compared to strong gravitational processes happening in the vicinity of a black hole. So we will stop on this construction. There are also other modern constructions of the charge definition. So there are also other modern constructions of the conserved charges. There is, for example, a solution phase space method, which has the benefits of ADM construction together with actually being covariant. However, it requires more discussion of the symplectic geometry, and we will not stop on it here. So let us recall the ADM decomposition, or that is the 3+1 split of the spacetime. So the metric is given by ds squared equals minus n squared dt, where n is the lapse and the metric on the spatial slice. Dt dxj, where ni is the shift. Where ni is the shift. The action for the gravity is given by S equals d4x of the four-dimensional scalar curvature times minus j equals to dt d cube x of the square root of h n of the following quantity. So we have the three-dimensional Ricci scalar plus the curvature. Plus the curvature and plus some surface term. These surface terms comes from the decomposition of the four-dimensional Ricci scalar in its three-dimensional parts. Namely, if we wrote all the terms here explicitly, we would also have covariant derivatives of the lapse of the shift. We would have also covariant derivatives of the shift. However, they are the total derivatives, and therefore they are the surface terms. So in the Hamiltonian formulation, we must first find the conjugate momenta. So recall that geometrically, the evolution of the metric on the space slice hij is given by 2n kij plus di and j plus dj and I. From this, we can define the conjugate momenta Pij equals to the variation of the action with respect to the time derivative of Fij, which is square root of h kij minus the trace of k hij. The Hamiltonian is then h equals d cube x eij plus the surface terms. So plus surface term here, plus the surface term from rewriting the ni hi explicitly, because the ni was inside the derivative. So plus surface term from rewriting the Hi. So the H and Hi are the Hamiltonian and momentum constraints. This can be seen from the Hamiltonian itself. Notice that N and Ni appear as the Lagrange multipliers. They're not within the H and Hi. And varying with respect to them, we would have the H and Hi to vanish. So let us remind ourselves that H is given by minus the three-dimensional Ricci curvature. Minus H minus 1 Pij plus 1/2 H minus 1 Hij Pij squared. Hi is then minus 2Hik dj Pjk. This is the momentum constraint. We know that H equals Hi equals 0, which we saw to be a constraint on the initial data in one of the previous lectures. The other equations of motion are then given by, well, as usual for the Hamiltonian setting, Hij is the variation of Hamiltonian with respect to the conjugate momenta, Pij, and the evolution of the conjugate momenta is the variation of the Hamiltonian, is the minus variation of Hamiltonian with respect to the metric Hij. We want to calculate the energy of the solution, and we naturally associate it with the Hamiltonian. So notice that on shell, on the solution, the main term of the Hamiltonian, which gives rise to the equations of motion, vanishes. And the energy is given by the surface terms. This leads us to an interesting observation that if you consider a closed universe, that is the universe that doesn't have a boundary, naturally all surface integrals would be 0, since there is no boundary, and the integral is, well, just 0. So for a closed universe, even in the presence of matter, the total energy would be 0. So total energy would be 0. This naturally leads to quite interesting cosmological speculation, is that if the universe is closed, then the total energy is 0, which is preserved, and it could appear from different quantum processes. Okay, so we want to find the energy, and we need to consider the surface terms. So let us simplify their form by looking at how taking the chart in the vicinity of the infinity. in the vicinity of the asymptotics. So since we are considering asymptotically locally flat spacetimes, they would look like Minkowski at the infinity, and we can introduce the adapted chart. So let us write as at r going to infinity as ds squared Minkowski at the infinity plus the O1 over R terms, where this is naturally the minus dt squared plus dr squared plus r squared d omega squared. And R we naturally, and the asymptotics is naturally at R going to infinity. So this gives us the following fall of rates. So we see that Hij is delta Ij plus O1 over R. Its conjugate momenta, Pij, is necessarily R minus 2. The lapse function is 1 plus the correction. And the shift is O1 over R as well. So the boundary terms are integrated at the spatial cross-section of the asymptotically flat end. That is of a two-dimensional sphere at the infinity. So its area element, ds of s to infinity, is r squared sin r squared sine theta d phi plus corrections. Plus corrections. Finally, let us also write the normal to the asymptotically flat end as ni equals to minus d over dr, so that we have the metric at infinity and we have ni, the inside going normal. So recall that we have two types of the surface terms. The first type came from rewriting the scalar curvature, the four-dimensional scalar curvature in three-dimensional quantities, and the second type came from rewriting the Hamiltonian in the NI-HI form. One can see that using our fall of rates, the second type of the terms is subleading, that is vanishes at the infinity. So one can see that boundary terms for chi the only relevant boundary term comes from the rewriting the curvature, the scalar curvature, and we naturally have it as, and we will naturally call it the ADM energy. So the ADM energy, the surface term, non-vanishing surface term at infinity, is given by limit of r going infinity of the two-dimensional sphere ds sum over indexes of ij and I d j h ij minus d I h j j. And the full Hamiltonian is h plus the ADM energy. There are two things to note here. First of all, one can show that the ADM energy is the Komar mass. Secondly, using the chart we have constructed, we can write the ADM energy as one of the terms in the expansion. So we write it as the metric as the Minkowski part plus 2 plus other terms. Okay, so similar to the ADM energy, we can define the ADM momentum. So we can define pi equals to 1 over 8 over pi, limit r going to infinity, of s to r ds kij and j minus k and I, where here was the sum over j. Now, naturally, one can ask, one can ask if we can have spacetimes with negative ADM energy. We can indeed find such spacetimes. So, for example, if the ADM energy is the Komar mass, and we know that for the Schwarzschild solution, the Komar mass is the parameter m. If you take the negative mass Schwarzschild, that is the naked singularity, we would have negative ADM energy. However, from the previous lectures, we have understood that naked singularities are not particularly physical and are not particularly welcome in our nice settings. So naturally, we come with the positive mass theorem. The theorem was shown first by Schoen and Yao. Yao as in Calabi Yao. And completed, generalized by Wheaton in 1981. And this is called the positive mass theorem. So, namely, if we take the asymptotically flat initial data, asymptotically flat, geodesically complete, initial data, and we take matter satisfying the dominant energy condition. Then we have the ADS mass. Then we have that the ADS mass is bound from below. That is bound from below by the square root of the square of the ADM momentum. The equality is achieved only for the Minkowski spacetime. So the natural consequence of the positive mass theorem is the Lichnerovich theorem of the absence of the gravitational solitons in the vacuum case. So the statement of the theorem goes that if you take vacuum asymptotically flat, that is cosmological constant equals 0, solutions which are strictly stationary, so vacuum strictly stationary spacetimes must be static, and by the positive mass theorem Minkowski. So let us explain the meaning of the theorem. The original statement by Lichnerovich was that if you take the vacuum lambda equals 0 strictly stationary spacetime, that is a spacetime where we have a globally defined stationary killing field, then the spacetime must necessarily be static. And the positive mass theorem allows to conclude that a static vacuum, that such a vacuum spacetime would necessarily be Minkowski. So, what does it mean to have a globally defined timely killing field? So it means that it's not a black hole spacetime, because for the black holes we have horizons on which the timely killing field some timely killing field becomes null, and in other words, this means that horizonless, purely gravitational configurations cannot exist. So in other words, some gravitational cusps that can be interpreted as gravitational solitons cannot exist in vacuum lambda equals 0 general relativity. This is another argument for the black holes to be universal type of solutions in general relativity. I should comment that in the presence of matter and for non-zero values of the cosmological constant, such solitons can exist. For example, it is known in 5 dimensions that taking the negative cosmological constant and an electromagnetic field, we will have a well-defined smooth soliton. Similarly, in a 4-dimensional setting, if we couple Einstein to Young-Mills, we will have countably many families of the solution. Some of them would correspond to solitons. This abundance of the solitons in such cases would also affect the uniqueness of the black hole theorems. Would also affect the uniqueness of the black hole solutions, because if we have such solitonic configurations, one can think that one can add a solitonic configuration, figuratively speaking, onto an existing black hole to get another black hole solution. And this is one of the arguments that the black hole uniqueness theorems usually work in the settings when the Lechnerovich theorem is also correct. In the next lecture, we will naturally discuss the black hole uniqueness theorems in more detail, and we will finally do the link connecting the event horizon of black hole, which is a physical but a global notion, to a geometrical but a local notion of a killing horizon.